This video contains solutions to the motion in space practice problems. For this first one, we're given a formula for the position of an object in vector form, and we're asked for the velocity, speed, and acceleration. So we know that if the position is given by r, then the velocity is just going to be r prime. And again, when we take the derivative of a vector-valued function, we just take the derivative of each component. The derivative of 3t squared is 6t, and the derivative of 4t squared plus 3 is 8t. So that's the velocity formula. The speed is just the magnitude of the velocity. And that's going to be the square root of 6t squared plus 8t squared. That's 36t squared plus 64t squared. That's 100t squared. And when we take the square root of 100t squared, we get 10 times the absolute value of t. Finally, the acceleration is the derivative of velocity, which also happens to be the second derivative of the position vector. And the derivative of 6t is 6, the derivative of 8t is 8, so that's our speed, velocity, and acceleration. This time we're going backwards. We're given the acceleration function, we're given an initial velocity and initial position, and we're asked to find the position vector. So we're just going to integrate rather than take derivatives. If we know that a of t is 1, 0, 2, then we know that v of t is the antiderivative of a of t. Velocity is the antiderivative of acceleration, so that's going to be t, 0, 2t, plus some constant vector that we'll call c. Since we know that v of 0 is the vector negative 4, 1, 3, plugging that in lets us figure out that our velocity vector is t minus 4, 1, and 2t plus 3. Finally, our position vector is the antiderivative of the velocity vector. Taking the antiderivative of each of these components, we get 1/2 t squared minus 4t. Antiderivative of 1 is t, and the antiderivative of 2t plus 3 is t squared plus 3t. Again, plus some constant vector. I've already used the letter c, so I'll use the letter d. We know that r of 0 is the vector 0, 0, 5. So again, plugging 0 into this formula for r of t, we end up seeing that r of t is 1/2 t squared minus 4t plus 0, t plus 0, and then t squared plus 3t plus 5. And that's the position vector that we're looking for. All right, now we get into a couple of word problems. And the setup for these problems is really important. So what we really want to do is try to rewrite these word problems in the form of what we were just working on. So we're given some initial information. We know that the projectile was launched from 20 feet high at a certain angle, and we want to know when it hits the ground. So we can do ourselves some favors here to make the math a little bit easier by drawing our axes such that our initial position is here at the point 0, 20. We can imagine there's our platform that we're standing on. And then we're launching the object up into the air, and we're asking where or when does it hit the ground. So we don't know what the x-coordinate is going to be, but the y-coordinate is definitely going to be 0. So the initial position, r of 0, is 0, 20. And then our initial velocity vector, we know that the initial speed is 250, and that means that this initial velocity vector, v of 0, is going to be 250 times the cosine of 60 degrees, comma, 250 times the sine of 60 degrees. And that's going to be 250 times 1/2, 250 times square root of 3 over 2. Or in other words, 125, 125 radical 3. Finally, we know the acceleration is the acceleration due to gravity, and so that's going to be 0, negative 32. Gravity pulls down with a force of 32 feet per second squared. This is all the information like what we had in the previous problem, where we had a formula for acceleration, we had an initial velocity, we had an initial position, and we put it all together by taking two antiderivatives, and we got our position function. So we're going to do that again. v of t is the antiderivative of a of t, so that's going to be 0, negative 32t, plus some constant vector c. Using our initial velocity information, that's going to tell us that our velocity function is going to be 125, and then negative 32t plus 125 times the square root of 3. Integrating that gives us 125t, negative 16t squared plus 125 radical 3t, plus again some constant which I'll call d. Taking our initial position information, that tells us r of t is 125t plus 0, negative 16t squared plus 125 radical 3t plus 20. And now again, what we're looking for is when does this object hit the ground? After how long will the projectile hit the ground? And so what we want to do is set our y coordinate, our y component, equal to 0 and solve. So that's a quadratic. We can use the quadratic formula. I cheated and used Mathematica to do this for me quickly, but I get two solutions. T is approximately equal to negative 0.09 and 13.62. Obviously, the negative answer doesn't make any sense in this problem, and so the answer that we're looking for is 13.62 seconds. All right, same kind of idea here, except we're not told the initial angle. So we know that our initial position is over here, and again, we're going to draw our axes to try to make our lives as easy as possible. We're going to draw this so that there are our x and y axes. So the initial position is at 0, 0. So r of 0 is the vector 0, 0. And we're interested in getting the ball to this point over here, which is 390, 40. And so the ball is going to be launched at some initial angle, travel in a parabolic arc, and then land in the hole. So since we don't know the initial angle, all we know about our initial velocity vector is that since we know the initial speed is 150 feet per second, it's going to be 150 times the cosine of that, whatever that angle is, and I'll give that angle a name, I'll call it alpha. So 150 cosine alpha, 150 sine alpha. So alpha's a constant here, but it's unknown. We don't know what alpha is. And again, our acceleration vector is a constant 0, negative 32. Integrating that, we get our velocity vector is going to be 0, negative 32t, plus some constant vector c. Using our initial velocity information, we figure out that v of t is then 150 cosine alpha, and then negative 32t plus 150 sine alpha. Integrating again, now being careful here, we've got two variables, alpha and t. We're integrating with respect to t. So the r of t, right, alpha is a constant, we just don't know what it is. So we integrate with respect to t, and we get 150 cosine alpha t, that's supposed to be a cosine alpha t, and then in the y component, negative 16t squared plus 150 sine alpha t plus some constant d, and then since our initial position is 0, 0, we can plug in t equals 0, and we get that d is just 0. So we get our position function is r of t equals 150 cosine alpha t, and then negative 16t squared plus 150 sine alpha t. So again, here's the position function that we found. And again, what we want is for the x component to equal 390 at the same time that the y component equals 40. Remember, 390, 40, that was the coordinates of the hole that we're trying to get the golf ball into. So that gives us two equations, and we can use Mathematica here. This is not a set of equations that we can really easily solve on our own. So using Mathematica, we end up with two solutions that have positive values of t. So remember, anything that comes up with a negative t, that doesn't make any sense in this problem. So the two solutions that we get are t is approximately equal to 2.83, and alpha is approximately 0.4074, and then t is approximately equal to 8.65, and alpha is approximately equal to 1.2656. Now to check the reasonableness of this answer, remember those angles are in radians, as they always are, and so if we convert those to degrees, just so that we can kind of use our intuitive notion of degrees here, we get 23.3 degrees and 72.5 degrees. And we can see that these answers make some kind of sense, because if we hit the ball at a low angle of 23 degrees, it's going to go sort of directly to the hole and get there in about 3 seconds. But if we hit the ball at a very high angle, it's going to travel much farther. It's going to take almost 3 times as long to get there, but it's still going to be able to land in the hole. So we see our two answers here, makes sense.